Math 1 class, Professor Blumenfield's class. They're going to give a presentation today, getting to the root of it all. As far as I know, what this represents is a program that you guys have created as students and with a little bit of faculty help, working on answering any root, right?
We'll explain it.
Yes, great. All right, so I'm the Math Club president, Jake Lakers, and I'd like to thank you all for coming today. This will last until about 3:50, and at that point we need all the Math Club, Math Society members to stay, and that's when we'll have our little meeting.
So Math Club members, please stay after the talk for 10 minutes for our regular meeting. Okay?
And then after that we'll have food outside for any of you guys who would like.
And others, please save some food for the Math Club members.
Please give
Thank you. It's my pleasure to welcome you to this event, Getting to the Root of It All. This is the result of roughly 3 months of very hard work in my Calculus 1 class, and I'll give you a little bit of background to how this began. It's really Ryan Jones's fault over here for giving me a hard time. Every time I teach something, he'd ask, well, what are we doing this for? What's this useful for? And I kind of took that challenge personally and developed a project that was for extra credit, so they didn't have to do it. But we got nearly the entire class on board. And the aim of the project was to take a topic in a calculus class, specifically Newton's method for root finding, which we don't spend a whole lot of time on, and to expand upon it and have them look at alternative methods besides that method, and also explore not only the theory behind the method, but also kind of the strengths and weaknesses of each method, and develop their own code using some open source software that was free. So we tried to stick with free stuff the whole way through. And they ended up producing a roughly 40-page booklet, which is right here. These are available. If you haven't gotten one already, they'll be outside. It's called Getting to the Root of It All, and it summarizes all their work, including the math and the code. And 5 folds, and they put how many hours?
A lot.
1,000 hours on it. We've pretty much been living at Starbucks and various locations working on this. We're really excited. We have a competition coming up this weekend in Monterey at a regional math conference, and we'll be competing with other schools from Northern California, and we'll represent the first Boston-Cetus math competition ever. So I don't want to talk too long. The students are really what this is about. So I'm going to turn this over real quickly. Let me introduce the project leader, one of 2 leaders, Chris Williams. And he is a business major. His goal is to transfer to the Haas School of Business at UC Berkeley. So I'm going to hand it over to you.
How are you guys doing today? My voice is very low right now, so let me know if you guys can't hear me. As you guys know, we're a calculus class. There's a lot of math involved when it comes to calculus. However, like Blumenfeld was talking about, the entire project is not just math-based. There's a lot more that goes into there. I've said this before during the invitation. I want to kind of reiterate it one more time, is that I look at math not just having to be math in general, numbers with some letters attached. It's a lot of problem solving, and it can be used in plenty of different areas of fields and expertise. Before we get into the math and computer programming, I kind of want to reach out to all the leaders in the field and people who want to be future leaders about how, no matter what you're learning or teaching or presenting, everything is based around organization and a great team. And that's what we have right here today. So first thing is, again, Professor Howard Blumenfeld. The main thing I want to talk about, though, is the class profile, which is going to be 4 parts. We have a lot of engineers, a lot of the future people who want to work in physics, chemistry, like myself, business. We have about 3 business people in there as well. And with this level of math, a lot of us are looking also to go to the Haas Business School further. The challenge at hand, complete a 4-part project. Explore alternatives to Newton's method, such as Zhang's method, which we'll attach later today. And create a few free computer programming for future educational use. The second part is to write an investigative research paper. That's going to be that 40-page booklet that we have at hand. Hopefully all of you guys get it today. The third part, document all the work and research performed. And the fourth part, what we're doing today, present to you a nice little 2-minute speech. So we considered it. We thought about it. Not everyone joined, but a lot of people did. We accepted the challenge. There's 4 parts to this, again, not math-based yet. The first part is understanding what Blumenfeld told us. You can't start anything unless you understand what you've been told. Second part is having a common goal. The third, organization. And the fourth, the ability to access technology. Again, no matter what field of expertise you're in, these are all 4 parts that you need to have before you can start a project. The first 2, understanding the task at hand and having a common goal. We can kind of summarize that with our mission statement. I'm going to read this along with you guys. As a team, we will collaborate in our efforts to create a computer program that will utilize the efficient root finding techniques known as Zhang's method. We will demonstrate when the use of Zhang's method is more beneficial in circumstances compared to other root finding techniques, such as Newton's, bisection, secant, inverse quadratic, and modified Newton's. We're going to do this with in-depth research and accurate examples. We have the computer sleeping on both sides. Once created, we're going to present our computer program to the public without cost. Again, we did a lot of this for free. We want to give that back to the educational field so that people can build upon it, and they can do so without having to worry about financial aspects. And we're going to do that again with free software we're using today. Going into organization, 4 teams. We call ourselves the pros. We're programming, we're research, organization, and support. Programming, of course, develop a computer program based on the mathematical root finding techniques. The second, research. Create a foundation for mathematical reasoning based on historical examples and also proofs. Operations, oversee many aspects of the job, and also document it so we can manage it. You can't manage when you can't add together, so we need to be able to perform. And then support, edit, and create a platform for what's been researched. The fourth part, the ability to access technology. Again, everything's computer programmed, so we need to have the ability to actually program it on the computer. By doing so, we're going to be using Facebook. As you all know, it's free. Perfect way to do so. It's a great way to add to the meetings and being able to have conversations instantly. Second, Google Drive. That's where we created and shared forms, documents, and presentations. The third is our Dropbox. Got cut off, but Dropbox is also free. I don't know if any of the teachers here use it currently, but it's a great way to share information and forms. Anytime you raise your hand, I have to stop talking. I know that in your tax class. As you guys know, this is a Facebook page. Just using it around, again, Ryan, our main computer programmer, and Howard, have a little conversation going on. You guys can see my top 4 things as well. But this is the main part too. This is the Google Docs that we use in Google Form, and we used it anytime you were going to perform work. You just open it up on your phone, open up your laptop, open it up on your iPad, and it was just a couple simple questions. And it asked, what team are you out of 4? Who's in attendance, has a list of your students, and then what were you working on, and how many minutes did you spend doing so? What happened after this? It created a document that I can go back and so for Blumenfeld, and we can look, and we can guarantee what was being worked on. We can see the progress of what was being worked on. More importantly, we can look at the minutes per team. If you look at all the orange, you can see that's where the teams are located. The programming team is broken up in 3, that's why there's more than 4 on there. The overall group minutes spent, over 14,000 minutes. However, when you break it down individually, when you break it down by hour, we did nearly 360 hours worth of work on this stuff. In Dropbox, just to give you an idea, this is how much forms we put in there. And again, you have automatic attachments anytime you want to take a look at it. The programs that we use today that they're going to get into a little bit more with their math, we use LibreOffice. This is something we started off with, creating the projects, creating the platform, We ended up switching back to Google to get a lot of it done and also Word. But it's a great way to start, and I advise a lot of you guys to look into it a little bit more. WinPlot, the graphs that you see later today, they're going to be used on a free source. Generates graphic examples of functions, and it's a great visual of all the equations that you're putting in. You get to see it come to life. Maxima, it's a computer programming software we use for developing our own open source program. I'm not the best at talking about it. Again, Ryan and Mark are going to get a little bit more into it. And fourth is going to be our GIMP, graphic editing software, which helps create the project booklets and also the poster board. So if you guys are interested, you guys can follow us actually while we do the speech. You guys can make comments on it later on. Go to Google Sites. We have one up known as Know Your Roots. Again, it's another free platform teachers and other leaders can use. But you'll see it on your booklets. You'll see it on your booklets. You'll see it online. Go ahead and please add any comments you guys have. We also ask for you guys to build upon what we present to you today. This is just the beginning of what you can do with the computer program. It's just the beginning of what you can do, finding the roots, finding really incredible equations. So please do so. In the meantime, I'm going to give it back to Blumenthal.
I'd like you to thank Chris here. Chris is a phenomenal leader. I mean, leadership actually started with Chris Southern in the back. Chris, can you stand for a minute? I want to just briefly call attention to Chris Southern. He's the ASLPC president, but beyond that, he's one of the best students I've ever had. I've had him for 3 semesters. Things didn't quite work out this semester, but he actually is the one who got me using Facebook in my classes.
Right.
And if it weren't for him, this project probably would have never happened, so we've been stubborn about it. But thank you. Yeah, you did. So it's a great pleasure that I get to introduce the next individual, a shining star in the math. Well, everybody's trying to get you into their department. A shining star in the business department. Her goal is to transfer to UC Berkeley in business administration, and she has worked on every aspect of this project. She's done programming, she's done research, she has done just about everything, and really impressed with her. Please welcome Jessie Bowens.
Hello everyone, I'm nervous. So I'm going to talk about the mathematical root finding methods, and you'll start to see how big our project was and why it was so important that we had teamwork and communication through social media. So let's talk about math. That little guy back there. We're not going to discuss all of this in our talk today because we want to make it a little simple and easy to understand so everybody can get it. But all of this information can be found in our booklets and on our Google site. So we had to research the historical backgrounds of all of the methods, analyze the advantages and disadvantages, give simplified explanations, and provide examples. So the methods that we did cover was bisection method, secant method, Newton's method, modified Newton's method, and inverse quadratic interpolation. So I'm going to talk about bisection method first. What bisection method does, you'll see all those lines, I'll explain those, is it takes 2 points at the ends of a function and then it divides it in half. Now if the function crosses the x-axis, that means it will be positive up here and negative down here. So it multiplies the end point and the middle point, and it sees if the answer is negative, which means that it did cross the x-axis and there is a 0, which is what root finding is. We're trying to find zeros of functions. So it keeps doing that, it cuts it in half, and once it finds the interval that has crossed the x-axis, it cuts it in half again, and again, and again. And that's how it gets a smaller answer of where the function actually equals 0. So the advantage is that it never diverges. In other words, it never goes further away from the root. It always gets closer. So it decreases error with every calculation as it gets smaller and smaller. It would take a lot of work if we did that manually, and we want to calculate it any number of times to get the answer as small as we want, which is why we had to turn it into computer programs so we could do it quickly. The disadvantage is that it converges slowly because it always has to cut the function in half, and if there are 2 zeros next to each other real close, it's hard to evaluate because it's crossing over and over again. The next method is secant method, where you find, once again, 2 points on the function, and you create a line in between the two. And wherever that line ends up crossing the x-axis, you go drop down or you move up, and you create another point on the function, and you connect another line. And you do that again and again until it gets closer to the root. The advantage is that it does not require an evaluation of the differentiated function. And the differentiation of a function just tells you the slope of the function. But that slope answer will be another function. So it's another thing you have to evaluate. So the fact that it doesn't have to do that makes it a little easier on the computer. And it computes faster with fewer evaluations. So it gets to the root quicker than bisection method will, because it doesn't have to cut it in half. And it fails to converge when the 2 points form a horizontal line, because it will never cross the x-axis. It just keeps going across. And it fails to converge when the x-intercept of the secant line leads further away from the root, so it just keeps going and going further out there. Newton's method only needs one initial approximation because it takes the tangent line. So it uses the differentiation of the function, and it finds the slope at a single point and creates a line. Wherever it crosses the x-axis, it then goes back up to the function and does it again and again, and gets closer to the root. So it only requires one initial point. You don't have to find 2 points on the function. And an accurate initial approximation finds the root very quickly. For example, you'll see why it needs an accurate one with the disadvantages. The disadvantage is that it can evaluate slowly when the initial approximation is near a maximum or minimum point. So at a maximum or a minimum point, the function starts to either curve back up again or curve down again, which means that the slope is going to be really small. Because if it's up here and you choose it at the top, it'll be a horizontal line again, and that won't work. And if it's anywhere near that, it'll be an almost horizontal line, and it'll take a lot of calculations. So it fails to converge at evaluations of horizontal or vertical tangent lines, because then we'll just keep going up and down. And it fails to converge when the x-intercept of the tangent line lands on a cyclic point of a periodic function. That was a little hard to explain. So it would just keep bouncing back and forth pretty much, which is the same thing as the next one. It fails to converge when the x-intercept of the tangent line as a point on the function has the same slope, because it'll go down and it'll come back around. It'll keep doing that. You're going to have to take my word on this one. It's called root jumping. And Daniel is going to talk about the rest of the method. Thank you.
Better be paying attention. It's worth 60% of your grade. Okay, I'm lying, there's no test. Wow, she's great, isn't she? We want to convert her to the math department. But no, very happy for her. She's a shining star on this campus. And speaking of stars, it's with great pleasure that I get to introduce Daniel Prentice, another brilliant member of my class. His goal is to become a physics major, which is what I started out as before I realized I wasn't very good at physics. And he wants to go to UC Berkeley as well. And I have no doubt that he'll get in there. And he has been tremendously helpful. He was kind of the jack of all trades. We just stick him on whatever was difficult. We'd say, oh, we can't figure this out. Where's Daniel? Send Daniel in. Daniel's also a military veteran, so I can make the joke we'd send in the troops, But he's a great student and a brilliant mind, and I'm sure that he will do very well in physics. So let me bring him up here, and he'll talk about what his part of that.
He was joking about that. That's the last thing I need is another test. Thank you. So, the first part I'm going to talk about is modified Newton's method. And it's the same as the Newton method she talked about, but it takes in the multiplicity of the root into account of the equation to pick up the pace again. What does it say? So when you're going towards the root, the maximum or minimum, the steps you get closer and closer to the root because of the small
just takes a long time. Not cool. So you can fix that, but you gotta know the multiplicity. And knowing the multiplicity is actually kind of difficult if you don't know what the root is itself. Kind of a chicken and the egg problem. I can really figure it out, but whatever. Yeah, difficult without knowing the root, but if you do know, this is actually a really great method. See, I like that. So here we go. Turn it off. Here we go. M is the multiplicity, and it's the same as the Newton's method regular, but we have that M. You throw it in there, and in this next slide, I believe it is, there's a picture. Shows you the difference. It works like magic, I'm telling you. It's awesome. And there you go. All right. So this is an equation of a parabola shifted over 1 unit to the right. These blue lines with an initial guess to the root of being 3, which is only 2 units away from the actual root itself. And you can tell there's about three iterations, movements towards the root from regular method, and it's only right about there. And I mean, I didn't put them on there, but it's going to take a long time. You're going to get closer and closer, and they're going to get more and more horizontal, and then it's going to be this big blue mess. Not nice. And then we have red, which is modified Newton's. When you take in the multiplicity being 2, you put it in, and one relation right there. Pretty sweet. I like it. But once again, we have the problem of finding the multiplicity of that root, and Ryan's going to talk about that in a couple minutes. As much as I'd love to beat my head against the wall, I'm trying to figure it out for a week and a half straight. The other method is inverse quadratic interpolation. It's a fun word to say. I call it IQI. A lot faster. The way this works is we take 3 different points on our function, and you put a parabola that goes sideways. And the reason you do going sideways is because you go up and down, you might not ever touch the x-axis. I'm sure that's somewhere you can do it with complex roots, but no. So if you do it in y, it's going to guarantee it has to touch y. It has to eventually get there. At least one time. So the way we do this is with this big, long, messy formula, but it really isn't that bad. You know, if you're in Math 65, you'll be able to follow this. I'm telling you, I was there a year ago. This is easy. I have a good example. So if we have the points 0, 1, 1, 0, 3, 4 as our three function evaluations, you just throw them in, simplify it, factor it. And this equation here is the parabola shifted up 1 unit and going towards the right. So I mean, this looks bad, but it's got more bark to fight over. So when you set y to 0, we'll get this value of here, x, the x value of the parabola. B is our current guess to what the root is, and PQ, which is these two equations here, which you plug in your y values, your different ratios of y values, and PQ is your adjustment to the root. So your next closer guess, because you keep doing this over and over and over, and eventually you'll get to your root, or you're going to end up, at infinity. All right. So here are three evaluations of f of x, and right about here, this is our new x, adjusted by q. So the way our program does it is we get rid of x or p0, and then you take this one, and that one, and you do a new parabola, and it's going to get like right there, a little bit closer. The problem with IQI is if you don't have a smooth function or it doesn't behave well, it'll divert really, really quickly and it'll go, not where you want it to go. And also, if you have your 3 y values on your points are the same, it doesn't work at all because you're just going to draw a straight line. And, that
why this method generally will not be used by itself. It will be used in conjunction with bisection and secant method. And now, Mark can tell you about programming all of these fun things we've been talking about.
Thank you, Daniel. Daniel has worked on multiple parts of the project like Jesse. He started out in the research team, and the programming team initially had, I think, 4 or 5 people in it, but it kind of whittled down a little bit to where it was pretty much just Ryan and Mark, and at the end they were having some trouble with some of the code, so I sent in the troops. And, well, we're still a work in progress. Thank you, Daniel, though. So I'm going to introduce Mark Bragg. His goal is to become a computer engineering major at San Jose State. And he has been a member and a mainstay of the programming team. So in calculus, it might surprise you that we're doing programming. Like, what? Why? Calculus is math. What does it have to do with programming? But a lot of the methods that we use in calculus and a lot of the things we teach these students, how can I put this? Technology serves as a very good supplement to helping them learn some of the concepts. It helps for them to actually see derivatives in action and to be able to generate really pretty looking graphs. We had this one graph called the bouncing wagon in one of our labs. It's kind of fun to look at. So yeah, math can be very fun and animated. And if you can't draw, you can have a computer draw for you. The right equation. Okay, so I'm going to let Mark take over from here. Mark's a really nice guy, and he's one of the hardest workers in this class. I mean, he always looks tired. but he's come a long way in the time that he's been with us, and he's definitely one of the shining stars in this class and responsible for the quality of our code being as good as it is.
So a lot of you might be wondering why we have these root finding methods. And one very good reason is it gets very difficult to find the root of like a cubic equation, because you have the quadratic equation, which is for finding like x squared plus 2x plus 3. You can find a root with the quadratic equation. But for an x cubed function, it's a lot more difficult, and it takes up about a whole whiteboard. Now, if you were to find 1 to the 4th power, it would take about all this, maybe a little bit more if you could keep it tight. So that's a lot of work to have to do, right? And 5th and above, you can't find those. It's not possible. Go ahead and try if you want to do it. So what we have to do in order to find those roots in an efficient manner is to approach it with these methods. And these methods are very simple, which is a really nice thing, because otherwise you gotta do that. Now, bisection method, that is the easiest one, I think. It's the oldest. And right here is your function, and these are your 2 parameters, like Jesse was talking about. And this might look a little bit like ununderstandable, like you don't even know what's going on because you don't know about computer language, but it's really simple stuff. So, first you put in your 2 parameters. That's all you do as a user. The program's already made. So you put in your function, and then you put in your 2 parameters where you think the root lies between. This is where the function happens, and it calculates the midpoint right here, and then it evaluates your 2 values, and then it calculates how to do the function or the method, right? It does the method for you inside of this function after evaluating all that. So you're not doing any of the math. The math is all done within the computer, and then down here, it tells the computer's telling itself, is this the root? Show the number. And then it also says, is it not the root? If it isn't the root, it runs through as many times as it needs to in order to find the root. That's bisection, pretty simple stuff. You don't have to understand it, you just have to know what it does. Secant. I like this method. I did this one, but then Ryan did it, and it was way better. So there's your formula, just like in bisection, and then you put in your 2 parameters. Now we go down to the function again, and it just calculates everything for you and does the equation needed to find the root. And then here again it says, is it the root? Does it equal 0 in this function? If it doesn't, it reiterates the calculations for you, and then it will print out the root as soon as it finds it. And there is also, like if you end up with that horizontal tangent line, it'll tell you, it doesn't work, so then you have to try new parameters. So that's secant, just as simple. And Newton's method, this one is a little bit more complicated, but it doesn't really require anything more from you because it has the derivative of the function, but it calculates the derivative for you. Very nice. So you put in your formula, but you only put in one of your guesses. You don't need two parameters. You just need one guess. So it brings in your function and your guess, and then it calculates everything for you here. See, and then it prints whether or not it is the root. So once it finds the root, it prints it out. And these are really cool functions. I like them a lot. And then inverse quadratic equation. Now this is, I don't like this. It's very complicated. So you have your same as the last time, formula, but then you have your three functions or your 3 points. Now we should use this. Now when it calculates all of these points, this all right here is just the function that Daniel was showing. These 6 or 7 lines right here, your x new, and it will calculate it over and over again, and it will take x new and it will replace this one. This one will replace that one, and this one will replace that one. So then it'll just keep putting in new ones, and they'll get smaller and smaller within the function. And again, it will find out if it is the root or it isn't the root, or if they can't find the root within these parameters. And it will tell you it is, or it'll tell you it can't. And now, to put it all together, that was a completely different situation, and it was actually really amazing how it all came together. And that was all thanks to Ryan Jones.
Thank you, Mike. Okay, so I don't know where to start with Ryan. I don't know where to start with you. Ryan came to me begging to get into my class. A lot of students do. Good. Not really. But he came begging to get into my class in the first week, and I told him, I'm up to 53. I don't know if I can take a 54th. And he stuck around and kept asking and asking, and finally got in. Then there was some problem with his registration. I don't know. He was perpetually late to class, even later than me, which is an accomplishment. But more than anything, there was something I saw in Ryan that reminded me of myself. We sat down in my office one day, and I said to him, what do you want to do with your life? And he was talking about his experiences in programming classes and interest in artificial intelligence and those kinds of things. And we got to talking about cognitive science. And that was something I dabbled with a little bit at UCSD, which, to make a long story short, I convinced Ryan, or he convinced himself, because he does whatever he wants to do, to major in cognitive science, at UC San Diego. So, and he has a knack for programming that is just amazing. This guy can talk pretty much, he can talk C fluently. He can go all the way down to assembly language and break it down in terms that are pretty easy to understand. Even I can understand with my very limited programming background. He's like the Daniel Prentice of programming for me. Whenever there's a computer issue, or if there's an issue with some code, or if I want to know if something's possible to do with code, I go to Ryan. Ryan will stay up till 5, 6 in the morning, messing around with programs and putting things in programs that shouldn't be there. What was Zangaran called before? And then I won't even go there. But anyway, Ryan is a superstar in this project. I gave them a very difficult challenge, which was beyond writing the code to these programs here for bisection, the secant method, Newton's method, inverse quadratic interpolation, I should say modified Newton's method. The two major challenges were as follows. So Daniel talked quite a bit about modified Newton's method, where you've got to determine the multiplicity, which is basically if you have a factorization like x minus 1, x plus 3, let's say there's a squared over the x plus 3, we would say that that negative 3 has multiplicity 2. So it's power that's above the factor. So one of the major challenges in trying to program modified Newton was determining the multiplicity of a polynomial. Very hard to do. Most programs that are out there that are written in MATLAB, Mathematica, you already know the multiplicity a priori beforehand by looking at a graph or something. You're like, okay, that has multiplicity, 3. And that just seemed kind of not as robust as I would like it to be. So I came up with a challenge. Hey, why don't you guys, this should be easy, come up with a program that determines multiplicity. And I put Daniel, Ryan, Mark on that, and they struggled like you wouldn't believe with it. They said, hey, we can't do this. I said, no, I understand. But then Ryan got obsessive. He started to not sleep, not eat, not shower. We won't go there. And he actually, as of today, he showed me some ideas that he and Mark actually, and Daniel, all three of them, had come up with. And I said, hey, I looked at it. I said, hey, that might work. You guys got something there. Talk to Colin. And then the other program that I was really impressed by, I gave them some, do you guys know what pseudocode is? If you don't know what pseudocode is, it's basically sort of like you're writing an English essay, and you have an outline, you know what you're going to write, right? It's like, here's my intro, here's my body paragraph, here's my conclusion. Pseudocode is kind of just a really rough outline, here's what I'm going to program. And I wanted to give them something that they could be proud of as they program this. Now, modified Newton is definitely a big one, but so I did some research and I found a modern root finding method called Zhang's algorithm, Z-H-A-N-G, hence the Bazinga. And I looked through the code, I looked through the math, and I said, hey, this is doable. Not easy, but doable. And I talked to Ryan about it, and I said, hey, you think you guys can program this? And he laughed at me. Blumenfeld thinks we're, capable of this, really? And he struggled. They all struggled with it. This is a very robust root finding algorithm. Ryan found that Zhang was very... Did you ever try getting a hold of him? No. He's in Beijing. He's actually a meteorologist, a climate scientist that developed this algorithm. So he said, oh, my code's great. It improves upon all these other old codes. And it turned out that his code was very hard to understand, and he didn't even say what he programmed it in. And he had some very weird operators and other things in his code that we couldn't figure out what they did. But then Ryan found another article of sort of an improved Zhang, and that even made Zhang go faster. And he wrote the program with Mark, and I don't know if Daniel was on the programming team at the time, but it works. The code is freaking long, but it's very easy to understand. And I think this is one of the most major contributions and biggest things we can brag about from this project. So Ryan's going to close out this part, and I couldn't think of anybody better to close it because he kind of was my inspiration behind this project from our conversations we had prior to me thinking it up. So please give a very warm welcome to Ryan Jones.
Hello, my name is Ryan Jones, and I'm the lead programmer for this project. I'm going to walk through the Zhang algorithm, which is a series of steps and instructions that uses the different methods. Oh, that's not right. It's not working. Oh, it is working. It is working. I'm just not holding it right. All right, I'm going to try not hitting more buttons here, okay? So the Zhang's algorithm basically goes through and it chooses which method would be best to do with the current balance that you have, and every time you run it, it can do a different method, and it will choose what's best each time. And it's an improvement on Brent, This guy named Brent, we did this algorithm back in the 70s, I believe, and it's very, very complicated. I don't know how he looked at it and was just like, this is good, I'm going to submit this to the public. It's very complicated to read. It's just been around a long time, and really complicated. I don't know, I'm going to confess, I still don't know how Brent's method works. But Zhang's is a lot easier to read, it's faster, and in a lot of conditions it can actually converge faster. He just improved it all around. He's totally got bragging rights about it. This is kind of like the pseudocode. I think this is a laser beam. There we go. The pseudocode basically walks through a couple steps here, really easy to understand. I wish I had a flowchart like this when I was trying to figure out Zhang. You start with your input, which is your function, whatever you want it to be, and bounds A and B. And part of the Zhang's rule, it has to cross the axis. It can't be like x squared, where it goes down and touches and it goes back up. You got to use different methods, like Newton's method for that. But if you have a function that does cross from negative to positive, and it's a real root, you can use Zhang. So that's actually what the error checking is. Is there a sign change? Is there one end in the negative and one end in the positive? Is either one of the bounds a root? Is f of a or f of b equal to 0? Because then you know, hey, you don't need to do anything. A and B are close enough together because some numbers you can never really round out. Somebody write out the full number of pi. You're going to be here a while, right? You can only approximate it because it goes on forever. So that last little condition there is just like, are they close enough together that it doesn't really matter at all? You can just say good enough. And then finally, there's a countdown to prevent infinite loops because this might go forever, possibly. That's how numbers are. They just go forever. They're weird like that. That's watchdog. If you read my code and you're wondering what is this watchdog thing, that's all it is. Countdown timer. So it checks those conditions. If those conditions are satisfied, it's going to continue. What it does is between A and B, it'll find the midpoint halfway in between that. So you got my fingers are A and B, and my head will be the midpoint. And once you have that midpoint, you calculate f of that midpoint. So now you have f of A, f of B, and f of C. And you know A, B, and C are three distinct different values. You don't have two that are the same because that would have messed up on that error checking part up here. It would have exited out right in there. So you have the three distinct values. Now, if you have three separate y values, if you have three, f of x, f of c, f of a, and f of b, if all three of those are different heights, you can make a parabola on it. And that's that inverse quadratic interpolation. Are the three f of x values unique? Yi is, I was doing this about 45 minutes before you all sat down. So if yi is, there are three distinct y values, we will do inverse quadratic interpolation using those values, and then we test it, because remember Daniel said that sometimes you get a value that's like way over there, and you don't care about that, forget about it. So if it is within A and B, if it's within that little window, then we'll keep it. If not, it's just thrown out and forgotten about. If two of the f of x values coincide, say you're doing like a sine wave and you happen to hit two corresponding points on the wave that are the same height, you can't do a parabola with that. It's just a straight line, not a parabola. So what it does is, it checks where the sign change happens, because you have your three values. It checks for the sign change between here or between here. Whichever little path has that sign change where it crosses, it does the secant method with those 2 points. Using the input. So if it's between C and B, it'll do secant method with C and B. Real difficult, right, guys? So moving on to the next slide, because pages have a certain size. Now there are up to 4 x values, assuming we kept that inverse quadratic interpolation one, which I'm calling S. I don't think I really made that clear. S is, C is the midpoint, S is the one calculated from either inverse quadratic or secant method, assuming that we're keeping it. And then A and B were just given to us at the beginning. So now we're just doing that sign change checking again. F of A and F of C and F of S first. See if the sign change is there. If you multiply these two numbers, a positive and a negative, the answer is always going to be negative, right, guys? That's about how difficult the math was for me with the program here. It's just like if, then, and multiplying stuff. Ideally, the root will be between these 2 points, because then the boundaries can move in on both sides, and that's great. That's where it can kind of be faster than Brent's method. If the sign change does not happen between there, or alternatively, if S was thrown out because it wasn't a good value, because it was way out of left field there, It's just ignored. So then we check for A and C. We check the sign change there, and then we check S and B. We just find the interval. Whichever one has that sign change, you just use those two values. So now, like, say the sign change happened in here. C and S are going to be the A and B, and we go way back to the beginning of that long presentation of my last slide, and we start over. And you just do that over and over and over and over again, and that's why it's a lot more fun to have a computer do it than you to do it by hand. So that's where it's a really big benefit of this, and it helps us out. And it just repeats as many times as we want. At the bottom of my slide here, I have links to the two documents, Zhenghui Zhang's original paper, and then Stephen Stage's improvements on Brent's method, or comments on the improvement on Brent's method. Stephen Stage's pseudocode, his explanation was a lot easier to understand, and that's where I really got my understanding of Zhang's method. I wish I had some nice, cool flowchart PowerPoint presentation to help me out, but you guys have it a lot easier than me now. That was Zhang's algorithm. Pretty much just repeats that over and over and over again. It's really easy when you look at it. Brent's method, like I said, I still don't understand it. So right there, that's a huge benefit. It can also converge faster and require less steps to find the point, which is great. It does have some limitations, though. If you don't have it in the neighborhood of the root, as they put it, nobody really defines that number because, you know, if you choose two numbers, there's an infinite number of numbers between that, because numbers kind of do that. So if we don't have conditions to satisfy it, we have to do something like Newton's method or modified Newton's method, which are more difficult calculations. You need to know the function, and you need to know the derivative of that function in order to use Newton's method. And that might be easy if you're just looking in your math book and they give you the function and you can do that. But I think the term that they used was called a black box function, where you're just like getting data and you don't really know what it is. It's kind of hard to calculate the derivative of a function when you don't even really know the function, because you're just like reading data. So that's why a situation like this, you don't need to know the derivative. If you don't have a nice crossing of a root, you need to do something like Newton's method, where things can get a lot more complicated. As Professor Blumenfeld was saying earlier, I did kind of get a little irritated when he said I couldn't do something, so then I went and I did it. And I have some pseudocode written out on a piece of paper I could show if anybody's interested on the kind of the steps I have for calculating the multiplicity of a root when you don't know it. But we do have the code up for modified roots where you do know the root, or the multiplicity. It's just a little weird to know that and not know the root. It's kind of like putting the cart before the horse. A little weird. That was it. Okay. All right. And, back to Mr. Blumenfeld.
Someone makes some concluding remarks. I'm excited to see what Ryan invents and what he comes up with when he works down there at UCSD in the cognitive science department. He has a lot of exciting ideas. He's definitely an innovator. Thinks outside the box, sometimes too much. Has to be contained. That's where Mark comes in. So I just want to make some concluding remarks before we make our transition here. First, there were many people from the class who made huge contributions to this project who didn't come speak today, and I just want to basically recognize each one of them. We'll start with Malia Gonzalez. Could you stand, please? Malia was the other leader. She led the research team, and she wants to transfer to Davis, Berkeley, or Purdue in mechanical engineering. Outside is another redhead. His name is Jimmy Benge, and he's a molecular bio and chem major with the goal to transfer to UCSD or UC Davis. Lindsay Vaughn. She is a geology major with the goal of transferring to UC Santa Cruz, and she is responsible for the booklet Looking So Damn Pretty. Nicole Torquato is outside, right? She was the leader of the research team with Malia, and she's a biochemistry major with the goal of transferring to UC Berkeley. And applause for Luis Garcia. He is a chemistry major. He's a member of the research team, and he dealt with big O notation. Yeah, right? His goal is to transfer to UC Davis, UC Santa Barbara, or San Diego State. And back there, doing the video camera work, is Zishan Khalid. He dealt with some really nasty math, convergence and other things. Involved math that you probably hope you never see again. He is a business management major with the goal of transferring to the University of Nevada at Reno. I can't say that. Nevada at Reno. Elaine Sala. Yeah, I guess Alan's the correct pronunciation. He is a biology major, really smart guy. I had him working on some very difficult math with me, and he actually comes from the Democratic Republic of the Congo, right? Yeah. And his goal is to transfer to the UC Berkeley in biology. I have one more introduction, but I'm going to wait on that. I just want to say, first of all, what a fantastic job my Calc 1 students did today. You have to understand, these are not all math majors, first of all, as you can tell. It's a very diverse group of students. And they were given a very challenging problem that I wasn't sure they could pull off when I first designed this assignment, all 6 pages worth of instructions. But they have astounded me and reaffirmed my belief that students can do stuff. Students are smart. The problem is not with the math students at all. We just have to learn how to direct them. And part of it is, one of my mantras in teaching has become getting where you fit in. And in my project, we had a multi-dimensional project. Some people were really good at technical writing. Others were good at programming. Others enjoyed math research, and so on. And we tried to get people to go wherever they wanted to go. And then we had the leaders. Chris, he wants to, he wants to go to the Haas School of Business, one of the top business schools in the country, and so does Jesse, and Malia also. She's not going to be a business person, but the 3 of them, they emerged as natural leaders. Chris Southern was our initial leader, and their job was pretty much akin to a CEO of a small company. If you look at the minutes, if you look at all the work involved in setting this stuff up, I didn't set that up. That was all them. Facebook was a huge tool. I don't even really respond to emails anymore. My students Facebook message me. I could be anywhere. I can, if a student has trouble with a problem, I'll whip out a napkin, start writing on it, take a picture, upload it, everybody sees it. I really feel like this is the direction we need to move in. I'm not one to preach too much, but I guess I am preaching here. I feel like social media is out there. Students are already using it. Why not use it too? Now, maybe I'm not using it in the best way, but I feel like it's important to meet students where they are, to learn about them, and to encourage them to push themselves to near the breaking point. Not to say, they can't do this, whatever. I think these students enjoy being pushed, and I want to wish them luck. 11 of them are coming to the California Mathematics Council of Community Colleges Conference this weekend with me in Monterey. And we're going to be competing against other schools. They don't stand a chance. Where we rock. Anyway, there's a couple things I want to let you know about. We have 2 programming challenges for you guys. And there's some pretty cool prizes. Well, cool by nerdy standards. The first one is called Stop the Zangarang. So Ryan and Mark's algorithm, they named it Zangarang. The name before you don't want to know. And basically we're challenging you to come up with an equation under certain conditions. It has to satisfy the intermediate value theorem. And you have to know that there's only one root on whatever interval you're going to plug in. And there'll be people out there to help you out with that. There's a computer already set up. If you can successfully stump the Zangarang, and Ryan will be out there deciding whether you've successfully stumped it or not, you will get a nice, Ryan, could you come model this for me? Bazanga button. That's right, because you stumped the Zangarang, and Ryan's going to take that personally, and he's going to try to improve the code. The other challenge is putting the fig in Newton. So modified Newton, we're still stumped on how to get multiplicity of a root. If I just plug in some random polynomial, it's quite complicated to be able to determine what the multiplicity of roots are that you're trying to compute. Obviously, you have to kind of go about it in a slightly indirect way. Ryan's got some ideas. We have not proven that it's worked yet or not, but it looks like it's going to work, but we're not sure. So if one of you comes up with a really cool modified Newton program that determines multiplicity in Maxima, in the language that we're, all this is done in our Maxima language, then we will basically take your code to the Creative Commons and get your name on it and try to get it included in the Maxima function of library of functions, which we're already going to try to do with some of these codes anyway, because they haven't been written before in this open source environment. We also are going to have some cake. We have a Bazenga cake. We have food, drinks. We got a cake of water. Sorry. I'm going to turn things over now to the only person I haven't introduced yet. She is the event coordinator for today. She brought the cake. She brought a lot of the snacks. She's going to be running around like a chicken with her head cut off. It's Sheila Naimyar, who come up here. She is a biological science major with the goal of transferring to Cal Poly.
Hi everyone. As you guys know, there are tables set up outside to pass out the pamphlets and booklets for you guys. And also there will be people, including myself, to answer any questions you guys have, and also for anyone to try out the hard programming problem. And also we have free refreshments, cake, chips, water bottles, drinks, everything else. And if you guys haven't already signed in, please do so at the table. And thank you for attending.
Yeah, thank you. You can follow her out. She will